Hello, welcome back to Transmission. Today, we welcome back Aaron Wade from Gaussian, a company that uses magnetic fields to enhance battery performance and enable faster charging and longer lifespans. The conversation explores the current state of battery costs and performance, recent innovations in Chinese manufacturing, the rise of battery manufacturing hubs, and solid-state batteries. What I found really interesting was the continued innovation that we're seeing in the battery space. For example, adding lithium iron oxide to a battery cathode to create a protective layer during initial cycles, enabling batteries to go up to 15,000 charge cycles. This industry has so much more potential for improvement. But with intense competition driving razor-thin margins across the battery sector, how will this shake out? Let's jump in. Aaron, welcome back.
Great to be back. Thanks for having me.
Of course. And we're going to go straight into a refresher from our conversation in last October. So we talked about battery costs a lot last time you were on. What has changed, or has anything changed since you were last here?
Yeah, so I guess as a small refresher, 2021, 2022, lithium prices went very high, battery production costs went very high, so that resulted in very high prices. And then over the kind of following 2 years or so, we saw a pretty quick decrease in the lithium price, and then cell costs and therefore cell prices came to about $40 to $50 a kilowatt hour. And then now, where are we? May
25.
May 2025. Cell prices are broadly in the same range. Lithium prices somewhat stabilized. There's been some innovation in the cell and some in the factory, but for the most part, the prices are pretty stable. And speaking to people, it seems like those prices are going to remain stable for a little while. There'll be obviously some fluctuations, but we're not expecting a really rapid increase or decrease over the next couple of months. Longer term, I think it's still likely that costs will come down, but kind of short term, they'll probably remain fairly constant.
It feels like a little bit of like calm after the storm, because we had this kind of period, as you say, from like 2022 to 2025, where it just felt like every time you looked at it, battery costs have moved and come down. And we went from sort of $100 per kilowatt hour down to sort of 40 very, very rapidly. And obviously that could never kind of continue at that pace, right? Because you'd go down to zero. But they have now stabilized, and we will see kind of a gradual continuation of the trend, but we're not expecting kind of that big jump that we saw.
Yeah, correct. So I guess a good industry to mirror is maybe looking at solar. And solar saw very, very, very quick decreases in price. And then over the next 40 years or so, you saw sustained decreases, but nowhere near the same pace. And you'd often have periods where maybe prices went up or were flat, and then some innovation would come in, slowly gain market share, and then everything would swap, and we'd have a bit of a decrease again. So I think somewhat constant, but still lots of innovation going on below the surface so that we're kind of ready for the next drop in prices.
Okay, then excited to talk about some of that innovation, and I will come on to how our battery design is changing. But before I go there, I just want to talk about how performance is changing. So of the cells that we're looking at today, how are they starting to operate differently in terms of like key performance characteristics like cycling?
Yeah, so I think cycle life is definitely a focus, especially in the stationary storage space. Energy density, I think at the cell level is maybe not so important, but definitely at the container level is super important. So we're seeing innovations at that level. So cramming more energy into the same box, or even as CATL have done, stacking two boxes on top of each other to get around that. But we're also seeing a requirement for longer cycle life enabled by some of the new additives that are being used.
Yeah, I wasn't sure if that CATL system was two 20-foot containers stacked, or whether it was like a high cube 20-foot shipping container. I actually don't know. I think it was a high cube.
Okay, interesting.
But as you're saying, so like a typical 20-foot shipping container now containing 9 megawatt hours, rather than what we would have seen a few years ago, like a 4 or 5 megawatt hour system.
Yeah, so I guess what we're seeing in the market is maybe max 6.5 megawatt hours, and then we see people like Envision or Canadian Solar aiming for 8, and then now CATL aiming for 9. But I guess CATL is interesting because the floor space is the same, but you've obviously now got a much higher container, whether that's 2 stacked or kind of a big one. But yeah, I guess as you put more energy into the same box, everything becomes cheaper because you have fewer extra components. So then it's a nice way to keep lowering the the price of the whole system over time.
Yeah. And is this like a relentless march to 10 megawatt hours in a 20-foot container?
Is that the goal? I feel like that may be the goal, and then someone will say they can do 10.02, and then everyone will be like, oh wow, okay, now we've got to aim for the next thing. So yeah, there's probably a target someone's set, but I imagine it will just continue.
Yeah, we'll kind of head through 10 and it'll just keep on going. Is everyone just kind of cheating a little bit on this? Like, did we get to kind of like 5 or 6 naturally, and then someone thought, well, I can call it 7 if I put the HVAC on the back of it, and I could call it 8 if I stick another bit on top? Like, are we actually getting better density in the cells, or are people kind of just shifting bits around in the box to try and kind of get a marketing level?
I think it's kind of a combination of everything. So there's definitely cell level improvements that can happen. There's also a lot of marketing that you can do. So maybe a good example is the cycle lives that are claimed. Nobody's actually testing out to that number of cycles. It's all assumed based on how the cells perform over maybe 1,000 cycles. So in reality, if you wanted to test for 15,000 cycles, it would take you, at the C rates that people are advertising, about 7 years to do that testing. But 7 years ago, the innovations that we're seeing at the cell level didn't exist. So it's pretty clear that people take those early cycles and extrapolate where they think the performance of the cells are going to get to. And other areas, maybe the zero degradation claims that people may have, where in the first 5 years, maybe you see zero loss in capacity. And that's much more likely to be achieved by over-speccing your energy stored. So you might actually have a 6 megawatt hour system, but only let 5 be accessible. So then over those first 5 years, you expand the window so that 5 megawatt hours is always available to people. So I think there's definitely tricks you can play to advertise your system as better, but there's also definitely this push for kind of optimizing at the pack level, putting more energy into the same space and increasing both the energy density and also the performance of the systems.
Okay, and let's talk about some of those design changes that are coming through. So in terms of different chemistries coming through, that element of sort of super long life batteries going out to 15,000 cycles, how is that happening?
So something I learned about fairly recently is the addition of something called LFO. So this is added as an additive onto the cathode side of the battery. So you mix it in with your LFP slurry, but it really helps on the anode side, so on the graphite. So during the first few cycles, this LFO moves over to the anode and helps form a better SEI, which is the protective layer on the graphite. And typically in cells without this layer may be uneven. So we have kind of thick bits, you lose a little bit extra lithium. And also lithium may not be able to pass through it particularly nicely because of the ratio of organic to inorganic solvents in it. But by using LFO, you get a much nicer layer. So this enables you to I guess, protect the graphite a little bit better and then reach these longer cycle lives that people are now aiming to do.
It's fascinating that you can essentially, it's going to be the wrong word, but like add elements to these particular chemistries and designs that essentially give you, for a small additive, give you a big uplift in terms of what that system can actually do. And I feel like the more that we run these systems, the more data we get in, the more innovation money that gets put into them, the more that we'll find these tweaks where effectively we can do things that give us improvements that are kind of far beyond a small addition.
Yeah, I think this is kind of highlighted by how early we are into the battery world, commercialized in 1991. So we're still relatively new in even using batteries in the real world, and even newer, I would say, in using them in ESS and EV applications. So yeah, I agree. I think there's so much innovation still to be done in improving the performance and then also helping to bring the cost down.
Yeah, I totally agree. I mean, we're only just now starting to look at using batteries for, actually, when we think about batteries then going into like power systems, we're only just about thinking about putting batteries in to provide inertia-like services. And that feels very much, that's really to do with the inverter rather than the battery cell specifically. But just as like another example of where we're 10, 15 years down the road, and only now are we kind of tipping over into that point where people now start to really use it. So totally agree. And we were also talking earlier about compaction density. What is compaction density?
So this, I think, became very popular back in maybe November 2024. And the idea is you want to put as much LFP material as you can in the same volume of space in your electrodes. So by doing that, the the amount of LFP is increasing for the same volume, but because your lithium is in that LFP, the energy that you can kind of carry is more. So then if you can put more lithium and more energy into the same size box, your cell energy can increase for a very minimal cost increase. So therefore your dollars per kilowatt hour can continue to come down. I think it's starting to become more popular. The way that it's done is twofold. So one is you need to change the particle size distribution. So if you think and you only have really big particles, there's going to be lots of gaps between the particles. So if you have particles of different sizes, some big, some small, the small ones can then start to fill the gaps. So then your overall density of your electrode is going to increase. But also you need to make your particles stronger. So the way that this is done is by adding a second sintering step. So you take your LFP material and put it back into a furnace, take it up to high temperatures. And this is where kind of a cost addition is of about 30%. So then right now, this kind of next generation of LFP is slightly more expensive, but the hope is that it kind of all gets put into one process. The production cost is the same, but then you're getting more energy out of your cell, so your cost is lower. But what I think is most interesting is this is starting to be rolled out, but people are already talking about the next level and the next level and where it can get to. So as this is, I guess, developed at material level, it's then passed on to engineers to optimize the production, and then the material scientists go and make the next level, and then there's this kind of conveyor belt of continuous improvement that will help bring production costs down very slightly, but that stacked over a couple of generations starts to add up pretty quickly.
This is like marginal gains in every part of the battery design, manufacture, how they're then implemented. Just going back to one thing you said around you're essentially stacking molecules in a particular part of the design, and then the compaction comes from trying to put them, maybe not put them close together, but add things to kind of fill in the gaps. What's going in the gaps? Like what?
So just more LFP particles. So if you think of an electrode, you have your current collector at the bottom, and then you have a certain thickness of active material with binder and conductive carbons to kind of stick everything together. But you just want to put as much material in theory anyway as you can in that space. So you'll have some pores for the ions to be able to move through. But then depending on what you're designing your battery for, so if it's a power versus energy cell, you're going to design it differently. But fundamentally, if you want to put as much energy as you can, you want as little wasted space and as much kind of material in those gaps.
And you're saying that the process of kind of filling in those gaps comes from essentially reworking that material rather than doing it under like my sort of basic mind imagines that you just like put it through some pressured process. But
so you do that as well. So in the battery production process, you do the first step, which is slurry mixing. So you mix your active material, your binder and your carbon into this wet mix, and then you coat it onto the electrode. And then today anyway, you dry the solvent off, called NMP, and then after that you put it between these two massive rollers basically to compact it down, called calendaring, to make it more dense. But that obviously has a limit, because if you put too much force, the particles then start to crack and break and the electrode starts to snap, so you can't do that. So there's kind of a limit to where those particles can go. So part of this increase in compaction density is making our particles stronger so they can take that force, but it's also filling in those gaps so that even when you've compacted it, there's just less of this kind of empty space. Okay,
compaction ticked off.
In great detail.
In great detail, and something that I think we'll see more on in terms of marginal gains. One last thing I wanted to run through with you in terms of just an update from the manufacturing and development side. So in terms of the recent mood music from China, what has been changing?
So I was in China, as recording a couple of weeks ago, when it published maybe a couple of months ago. And I think it's really interesting for a multitude of reasons. One is just the Chinese battery industry is absolutely enormous. It's so much bigger than I guess I thought, and maybe other people think as well. There's just so much going on. So I went to this show called CIBF, and I think there was 14 different halls full of different equipment makers, material manufacturers, cell manufacturers. It's just vast, and there's so much kind of companies and so many people dedicated to the industry. So I guess the first point is it really is huge. The second is that the Chinese industry is definitely suffering somewhat. I feel like maybe similarly to over here, there's been this kind of huge rush into the industry. So many people who make adjacent products or maybe have seen kind of the popularity of rushed in. So now we have so many people in the space, but because of that, there's this huge level of competition which is driving all these innovations. And it's very much a case of if you're not innovating, you're dying, which then means that the top manufacturers are innovating just as hard as everyone else. So their lead isn't, I guess, being closed up on. It's maybe even extended because they have more resources. So then there's so many people and so many companies who I guess are selling close to the margin with kind of little margins and close to production costs. And I wouldn't say it's a world where everyone is kind of going to go bankrupt imminently, but there's definitely kind of people struggling, and the industry is definitely taking a hit in terms of size and scale and somewhat mood.
Yeah, I think anyone who's kind of seen how many people have moved into, say, like the battery space outside of the manufacturing side, but into the route to market side, has seen some of this where in older agreements there was significantly less competition, and essentially there was a better split of sort of profit between asset owner and optimizer. And as more and more optimizers got into the space, it was quite an exciting space. You just saw margins become razor thin, and ultimately that ended up with lots of optimizers ending up being bought by much larger utilities. And I imagine that a similar thing to what you're seeing is that some of those innovators might end up going into competitors who have much larger balance sheets who could pick them up.
Yeah, for sure. I think it's interesting because there's almost two options, right? One is you buy the company for the IP. Two, maybe you invest in it so that the IP is still developed out of house. But three, I think on the battery manufacturing side, if someone has a factory that they built maybe 10 years ago, if you're CATL, do you want to buy that factory if that company starts struggling? Or do you just continue your current plan of building out what you already have? Because the chances are that factory is going to be very old, very manual, need a lot of work to be done. Whereas the latest CATL, BYD factories are just amazing. They're so automated, they're so clean, everything is so optimized that I think the incentive to buy these old factories and kind of take that company on board maybe is less so now. And then we'll see kind of people just carrying on with their production roadmaps.
I think to that point, we're also moving on to almost like the next generation of batteries in some way, or we may be, you tell me. Solid state battery manufacturing, are we moving towards solid state?
So I think we're always moving towards solid state. It's just how far out solid state is, which is always the question. So I guess 2 years ago, I was very much solid state isn't going to be a thing. It's too difficult. It's not going to work. And I guess two things have maybe started to soften my opinion. So the first was visiting some semi-solid state battery manufacturers over in China and understanding kind of that process. So there's a company called WeLion. So they supply NIO with batteries for their electric vehicles, but they also supply for stationary storage. And actually, it's one of their biggest factories is just for stationary storage. And they kind of have like a hybrid liquid solid cell. So you have your standard lithium ion cell, but you put some solid electrolyte in the cathode, some on the separator, some in the anode. You inject in a liquid, and then you do some form of solidification to then make some of that solid, and then you still have some liquid with the goal of removing the liquid over time and becoming more and more solid. So that route maybe will never get to 100% solid. Could get pretty close, and it's a pretty good kind of stepping stone to, again, every year, let's get a bit better, let's get a bit better, let's get a bit closer. And I found out from one person, so this may be not representative, but they're only kind of 10-15% more expensive than the conventional cells right now. I think I was under the impression that it would be 3 to 4 times as much, so $200, $300, $400 a kilowatt hour maybe. But if they're only a small percentage, maybe they're not that unrealistic to put in vehicles. And then the second, I guess, stepping stone is dry electrode manufacturing. So when we spoke about making a battery, typically you use that wet process. So you put NMP, which is a solvent, in and then dry that off. In dry electrode manufacturing, you don't put in a solvent, so you just coat directly onto the copper or aluminium. So at the show I was at, it was wild. They were coating electrodes on the show floor. So there was like a queue of people, and you'd go up and you could look over and see this going on. So this is, one, it would never happen anywhere because you're still breathing in the particles. But two, without the need for solvent, it is somewhat inert, so you can just do it out in the open without kind of needing these big dryer ovens. So you save a lot of energy, but you also save on safety because there's not this kind of toxic solvent around that can harm people. But that process is somewhat analogous to how you'd have to put a solid state electrolyte on your cathode or anode, being able to kind of get two non-wet things to kind of contact and stay together. So I feel like that, again, is a good stepping stone. So if we can do dry electrode manufacturing, it's now a smaller leap to doing solid state. So then all of these kind of innovations all somewhat stack on each other. So maybe solid state is still relatively far away, but there's definitely innovations that are being worked on that maybe will help us get some of the way there.
Okay. And I assume that thing that you saw in terms of the sort of pressing that was happening at the show, that was very much just for the show. That's not something that they were actually going to use the output from.
Oh, no, yeah. It was just for the show. So I went to their factory 3-4 days later, and the machine was already back in the factory, and they were starting to commission it to run with customers to practice making stuff again.
Okay.
But yeah, I assume that was just going in the bin, or hopefully to a recycling facility.
Yeah. Okay. Oh, good. And we jumped sort of straight into the solid state without really talking about what it is. So I just wonder whether we should just do the very quick pitch of like what solid state is, just at the most basic level.
Yeah. So a conventional cell has cathode anode separator, which are all solid, and then you have your electrolyte, which is wet, that you inject in, and this fills all of the pores that you have in your materials, and it's what the lithium ions move through to get to either side of the battery. Solid state, you replace that liquid with a solid, so then you still have your cathode and anode, but normally you have some of that solid separator in between to kind of blend it into the cathode. And I guess the real problem with it is twofold. One is the manufacturing, which maybe there's some level of solution. But the second is, if you have that interface, you have to keep it under high pressure to make sure you have that contact. When you have the liquid, it goes into the pores and it's very easy and you can just move stuff. But when you have a solid, that interface is far more important. So keeping that pressure strong and the interface there is important. But also you've got to have deeper within your electrodes good pathways for ions to travel through as well, which maybe is more difficult.
Super interesting. I think a few other topics from your visit to China that it would be worth kind of talking about a little bit. You touched on automation very briefly in terms of where CATL and BYD are going. Very welcome to sort of elaborate a little bit more on that. But I think I'd really like to get a feeling of the factories within China and in terms of their business development, where they're looking to send equipment to, how much of the focus is on the US, how much of the focus is on Europe? Is there a dynamic that's emerging there? What does that look like?
Sure. So I guess fairly briefly on automation. I mean, I think the first point is there's a huge range of automation in different factories. Some are very automated, some are not automated at all. So it really depends on your kind of size. But what we're seeing, I think, is a very clear trend towards more and more automation. So I think I used to quote about 50 workers a gigawatt hour as kind of high level. I heard that now 25 is what people are aiming for. So again, that's a 50% reduction in less than a year. And I think this will continue to come down because, I mean, robots never make mistakes. They don't unionize. You don't have to pay them once you've done the capital. So there's kind of a big incentive for these factories to continue to remove the labor to optimize. And the dry electrode people I saw, they covered about 50% of the production process. And they said they needed 2 workers, I think, to make 5 gigawatt hours, maybe 4 workers for 5 gigawatt hours. So it's like less than a worker a gigawatt hour. So there's really this push from both Chinese companies, but they're also looking to sell overseas. So companies in Korea or the US or Europe are also looking for this high level of automation to make factories, I guess, more efficient and cheaper. And then on the second question of where are people looking, I think, so when I was in China, I visited a place called Liang, which is a small city outside of Shanghai. When I say small, I think it would have had the second largest population in the UK. So still big, but small by Chinese standards. And CATL moved a factory there. And it's now a pretty big hub for battery manufacturing. There's quite a lot around it. So people are making machines. There's a lot of R&D. There's new companies popping up. So, and I think this happens quite often around China, where you have someone move and then the ecosystem develops. And I think this is interesting because I think we've seen this happen in Hungary, where CATL are moving there with a massive factory. BYD have announced that their European headquarters are going to be there. I spoke to a cathode maker, they're moving there. I spoke to an electrolyte maker, they're moving there. So I think it's likely that we'll see companies moving to these kind of hub areas if they're looking to export overseas. And then I guess with people looking for more locally sourced material, even if it's not a local company, if you can buy batteries from Hungary rather than shipping them from China, and they'll be the same quality, probably slightly more expensive, but maybe evens out with the shipping cost. I think it's kind of a clear incentive and goal for these companies to move overseas.
And we definitely talked about this hub concept last time, which is that if you build a single factory by yourself with no other hub around you, it's really hard because when something goes wrong or one key element of your manufacturing process, whether that's a person or a machine or a program goes wrong, it's very hard to then get in a replacement part quickly to fix that problem. Whereas when you're in the hub and there's 10 other factories all doing the same thing, then there's a little bit of, yes, you're in competition, but also you can work off some of the like local supply chain, e.g. for cathode or anode provision.
Yeah, and also it attracts the rest of the supply chain there with you. If you've got multiple factories, everyone's going to want to be in the same region because then they can supply multiple people. So I think it definitely makes sense that we're going to see this, and it feels like Hungary have won the battle.
Hungary have won the battle, and I'm gonna. This is horrible. I shouldn't do this. Your contrarian view last time was that local manufacturing was in some ways kind of spiraling the plug hole a little bit, in that without the volume coming through, it was never going to sort of land. And I think it sounds like Hungary is maybe going to make it work. Is that would you say that you do believe in local manufacturing, but provided it's the right people doing it and there's still this kind of hub concept that's setting up in Hungary?
So I think it's interesting because local manufacturing has its benefits, but the hardest part is actually producing if you've never done it before. So I think this is where a lot of the European factories and US factories and everyone who's new is really going to struggle, is being local isn't enough. People would always buy the cheapest and the best. So they'd always rather buy from China versus buy from someone down the street if you're 3 times as expensive and half as good. So I guess local manufacturing also makes sense, especially for things like electric vehicles that you're producing locally. If you're going to make the whole car and then ship the battery, why not just build everything in the same place? And I think there's kind of a desire, especially within countries, to bring that manufacturing to kind of local areas. But then again, it goes against the automation piece. So lots of states in America are trying to win factories to come to their state, with the, I guess, hope that this will bring a lot of jobs. But if everyone's massively automating their factories anyway, the amount of job creation is going to be relatively low. And you'll need more skilled workers, which maybe aren't coming from the host countries anyway. So I think, yeah, it's interesting.
Okay, and I promise that if you give a red hot contrarian view at the end of this episode, I will not hold you to account in future episodes. Okay, that's a really good update on our conversation from October, and I think people will really find that useful. Now I'm moving to you personally. You've moved. You're now at Gaussian. What is Gaussian?
So Gaussian is a spin-out company from University College London. So we've been around for about 2-3 years. There's 18 of us, and we're based in South London by London Bridge, in between London Bridge and Bermondsey. And what we do is we enhance battery performance. We remove compromise, and we do this by adding magnetic fields to batteries to increase fast charge, increase lifetime, and kind of let people not have to play around with that trade-off of wanting a cell that's high energy density, high power density, cheap, and can do crazy high C rates. So it's working on how we can help people have kind of the best of all worlds using our magnetic technology.
Okay, so this is using magnets to get batteries to work better. How does that work? Like, where do you put this magnet? Is it a series of magnets? Is it some fancy control software? How should I think about it?
So it's a combination of hardware and software. So the hardware goes as close to the battery as we can get it. So for some people, it's very close. For others, if you don't have access inside the pack, maybe you put it on the outside. But you essentially apply the magnetic field. You can do it during charging, discharging, one or the other or both, depends on what you're kind of optimizing for. And really the premise is you can lower the resistance within the cell by adding the magnetic field, but you can also remove kind of the hotspots that build up and more evenly spread the lithium ions throughout the electrode. There's actually a really cool video of a scientific paper that does lithium deposition with and without a magnetic field. So if you don't use a magnetic field, the lithium deposits, and then you start to get kind of preferential deposition, and then you start to get dendrites forming in kind of this mossy growth, which in a battery is obviously very bad because then you get a short circuit and a fire. But then when they applied a magnetic field, you got a very even and smooth and uniform layer. And we run with the same concept. They use permanent magnets, we use electromagnets, so we have more control and they're much smaller. But the idea is to kind of smooth that lithium out and enable this fast charging or longer life.
Okay, it's a super cool idea. We'll definitely put in a link to any video that shows the formation or not formation of dendrites. That's very much our target audience. I'm really interested that there seems to be two elements to it. So on one hand, there's this way of lowering resistance, and therefore the battery runs essentially with higher efficiency. But there's also this piece around the dendrites forming and deposits within the battery cell. So it almost feels like there's the short-term element of I can run at lower resistance, and there's the kind of longer-term element, which is I can prevent inefficiencies building up in my battery over a longer period. Is that how I should think about it?
So I guess it's kind of an optimization problem of how fast you want to charge and how long do you want the cell to last. And we have this with conventional batteries anyway, that on a spec sheet, you might be able to do 5,000 cycles, but you have to do it at very low C rates. And if you go very high C rates, maybe you only last 100 cycles. So we have the same trade-offs, but we can kind of enhance both of those. So we can take cells that aren't designed to charge fast and do kind of 5-minute charges thousands and thousands of times by both lowering the resistance and stopping these layers forming of dendrites.
Okay. And who is this being marketed to? Would I expect to see this on my iPhone, or would I expect to see it on my 1 gigawatt grid scale storage?
The short answer is kind of everyone. We're targeting people who have a real need right now for either fast charging or longer life, because we're still relatively early, but fundamentally it can be applied to any battery technology. So we're completely agnostic for the cathode chemistry, the anode chemistry, the cell format. So it can be cylindrical pouch or prismatic, which gives us a pretty wide net to be able to then work with anyone who wants to really enhance the performance of the batteries that they have.
Okay, and maybe let's just talk a little bit about the business case in this. So if I'm spending X on a battery cell, when I'm spending Y on Gaussian tech to go alongside it, am I doubling my cost? Am I adding 1%? Like, how is it working? How does the business case come through?
Yeah, so it's incredibly low, 1% or 2%, we think, on the cost side, because we're adding things to the pack. There's obviously a volume increase, which is typically kind of 3 to 5% increase in mass. Volume, sometimes 3 to 5% as well, sometimes 0, depending on the inefficiencies within the existing pack design. So there's definitely some trade-offs. That you don't kind of get a magic wand where you can have all these improvements with no trade-offs, but we think the increase in cost is very small, and the increase in mass and volume is so small that the performance benefits that we offer kind of outweigh that.
Yeah, the decrease in mass and volume, right? Because you're having to add your component to okay. So slightly more cost, slightly less volume in a 20-foot pack, but overall better performance. Mm-hmm. And if you were to put a percentage number on that, is that possible at this stage, or are you still too early?
In terms of percentage of performance improvement?
Say performance improvement.
So we can charge kind of 600%, so 6 times faster, and lifetime can be 8 times longer.
Those are totally crazy numbers.
Yeah, so it's like it is a huge improvement in performance. So it's not a few percentage. You can really go very quick or last much longer with the add-on technology, which is why the slight increase in cost and mass to your pack is kind of outweighed pretty quickly by those gains.
It makes me think, like, if you're CATL or BYD and you're putting in billions into these techs, into these projects, somebody comes along and says, oh, by the way, there's a company that's making you charge 6 times faster and giving you, sorry, I forgot the number on extended.
Up to 8.
Up to 8. Okay. So these huge improvements, if you're CATL, why would you just go and knock on that door and say, actually, you know what, this is so obvious, I'm going to have this for my next grid scale battery because I need this?
I think that fundamentally it's not quite as simple as putting a magnet on a battery. You have to do a decent amount of innovation. So we have about 12 years of total research on this, from kind of first concept all the way to where we are now. So you have to play around with things and kind of optimize. So then it's not, you probably will get a small improvement, but the level of improvement that can be offered is much greater if you have that kind of long-term experience. So, I mean, as with everything, I think as soon as you kind of put stuff out there, people will try and do it. So it's always kind of a race to optimize. But as far as we know, we're the only people doing it commercially. There's increasing kind of academic papers coming out on this, but we've not seen anyone else looking to do this.
Okay.
In the field.
I love it. Look, this is one of the things where you start to get volume, you start to get enough interest, you start to get enough academic institutions looking at this to give you 12 years worth of data. And all of a sudden you start to get things which you weren't expecting originally, which are adding on 5, 10, 15, 20% to performance. And this is a big part of the whole story of how batteries got so cheap and how its performance got so much better, so much more quickly, because there's a volume effect going on of just number of people, number of innovators looking at it. And so it's a real sort of story of the battery space encapsulated into one business. I now need to move us on to our final two questions, which is firstly, is there anything you'd like to plug?
So I think similarly to what I plugged last time, outside of all of the work I do at Gaussian, which obviously contact me if you're interested, is the stuff I do with Volta Foundation. So Volta Foundation is a non-for-profit kind of for the betterment of the battery industry. So we write a report every year called the Battery Report, not very originally named, but that kind of does what it says on the tin, which just sums up what happened in the last year in batteries. So it gives kind of timelines, but also data from kind of leading research houses on where costs are, what the supply chain looks like, all of this. So it's a really good read if you're interested in batteries. But we also put on events, we do webinars, and it's all kind of free and open to come to. So if you're interested in batteries, if you want to learn more, if you know nothing and just want to kind of chat to people who do know some stuff, come along because we're very friendly and nice.
Very good. And today we're actually hosting some of the Volta team coming and looking forward to squeezing as many battery heads into one room as we can. I'm slightly suspicious we don't quite have the space, and one of the local pubs is going to get a influx of battery nerds.
Some nice revenue for them.
Yeah, some nice revenue for them. That all works. Okay, Aaron, on to the last part, which is your contrarian view. So is there something that you believe that the majority of the market doesn't?
Yes. So I think we're kind of in a world where we have to make a choice between accelerating our climate and sustainability goals versus the onshoring and security aspect. And I think, I mean, especially the US right now, but I think it becomes more of a kind of topic that maybe people lean towards is we want to isolate out riskier countries and kind of onshore more and more aggressively. Whereas I think maybe a more logical approach is to welcome collaboration and really push to accelerate the adoption of electric vehicles, of stationary storage, because we have such a big opportunity to kind of do that as fast as possible with Chinese help. And maybe one example is if you want to work in China and produce vehicles, you have to make a joint venture. So Western companies can't come over and just start selling. They have to work with the Chinese companies. Maybe we do something similar in other regions where, yes, we welcome kind of this collaboration, but you have to do it with the benefit of an existing company. And then this will really help drive that adoption, keep the prices coming down. There are obviously some areas maybe where you wouldn't want this. So military applications, maybe you have kind of outside that open access. But I think collaboration is better for the world in general.
Mm-hmm. I think this is a growing trend for onshoring and looking to bring things within individual countries' supply chains, which onshoring is. But I think you like that is a growing trend. So the kind of call to go back to kind of most fundamental markets and best price for outcome should be dominating and should be winning, I think is contrary to that trend, which is interesting because I think that we will definitely have this conversation more and more as batteries become a bigger part of how they impact the whole market. Aaron, thank you very much for coming on. A pleasure as always. Looking forward to having you on again sometime soon.
Sounds good. Can't wait. Thanks again.